When most people think about crime, they think about stories. What happened, who did it, and why. But behind every story, there's data. And crime data isn't random. It clusters in neighborhoods, in time, and sometimes even within social networks. If you can map those patterns, you can start to predict them. That's the idea behind crime analytics, using data and modeling to forecast where crime is most likely to happen next. Today on Curious Modeling, we're going to pull back the curtain on how these systems actually work. Not the politics, not the headlines, just the math, the models, and the meaning behind predictive policing. Every good model starts with data, and crime analytics is no exception. Most police departments rely on a mix of incident reports, arrest data, and calls for service, those 911 logs that tell you what's happening and when. Then there's geographic data, GIS layers for streets, lighting, zoning, and even where liquor stores or schools are located. Let's not forget temporal data, what time of day, what day of week, even what season the crime occurred. Put all that together, you get a multi-layered picture of when and where crime tends to cluster. From there, analysts choose a unit of analysis. This is a grid cell, a patrol beat, sometimes just a single address. And then they clean and enrich the data, geocoding the points, adding lag variables like crime in the past 30 days, and engineering new features such as distance to the nearest prior incident. In other words, they're turning messy records into something a model can learn from. Now that we've got our data, let's talk about the simplest and still most common approach, hotspot mapping. The idea here is straightforward. Crime tends to cluster. If you map where incidents occur and smooth out the noise, you can identify the hot zones. This technique is called kernel density estimation, basically a mathematical way of asking, if a crime happened here, what's the chance another one will happen nearby soon? You also see methods like GOG statistics, which identify statistically significant clusters rather than just visually dense ones. And repeat victimization models, which use the timing of past crimes to predict when the next might occur. Hotspots and maps are intuitive and powerful, but they only tell one part of the story, where crime has been most visible. They can't tell you whether that hotspot reflects criminal activity or just police attention. Now to predictive modeling techniques. To go beyond maps, analysts use predictive models, algorithms that learn patterns in the data and output probabilities. A classic approach is logistic regression. It takes predictors like time, neighborhood characteristics, and prior incidents, and estimates the likelihood that a new crime will occur in a given area. It's simple, transparent, and interpretable. You can see which variables matter the most and to what level. But as data grows more complex, we often turn to machine learning models. Decision trees and random forests to capture nonlinear relationships, gradient boost models like XGBoost for even higher accuracy, spatial regression models that explicitly account for neighborhood effects, like how one block's crime rate influences the next. Each has its pros and cons. The more complex the model, the better it may predict, but the harder it is to explain. When it comes to policing, explainability matters. Because if an algorithm can't explain why it labeled an area as high risk, it's hard to justify acting on it. Not all predictive policing focuses on places. Some models focus on people. That's where social network analysis comes in, mapping relationships between offenders, victims, and associates to identify clusters of risk. This method looks for patterns like who has been arrested with who has connections to known gang members, who is recently a victim of violence themselves. The goal is to identify individuals who are statistically more likely to be involved in future violent events, directly or indirectly. Chicago's strategic subject list, for example, at the time of its usage, assigned each person a risk score based on those variables. It was data-driven, but also deeply controversial, because being connected to crime isn't the same as being responsible for it. That's where predictive analytics meets its ethical limits. The math is neutral, but the consequences aren't. Now to validation and performance. No model is complete without validation. Crime analytics, that means checking whether predictions actually match reality, and whether they do so fairly. Analysts use metrics like precision, recall, and AUC, just like in any machine learning task. But there's also geographic cross-validation, training on one region and testing on another, see if patterns hold up across space. Then there's ethical validation. Even if a statistical model is statistically accurate, does it distribute errors evenly? If the false positives, the predicted crimes that didn't happen, are connected in the same neighborhoods, that's not an error, that's bias. Now the emerging frontier. Crime analytics is evolving fast. Some researchers are using deep learning to analyze video feeds and sensor data. Others are building spatiotemporal Erase. Others are building spatio-temporal neural networks that combine place, time, and social context all at once. But the most interesting direction isn't necessarily more prediction, it's predictive prevention, using analytics not to deploy patrol cars, but to deploy resources, housing aid, youth programs, and mental health support, for example. That's the turning point for this field, moving from predictive policing towards data-informed prevention. Because at its best, analytics isn't about forecasting punishment, it's about understanding patterns deeply enough to create change. So next time you see a crime map, remember, it's not just a snapshot of risk, it's a model of the world someone chose to measure. And like all models, it's only as fair and honest as the data behind it. Found this breakdown useful? Subscribe to Curious Modeling for more explorations into how data shapes our world, sometimes how it shapes us.